Pluto is 3.67 billion miles from Earth. A radio signal traveling at the speed of light takes more than 5 hours just to cross that distance once. No human being has ever been there. Only one spacecraft has ever flown past it. That was a single flyby that lasted a matter of hours in 2015 before the probe kept moving and never came back. For 95 years after Pluto's discovery, scientists accepted that this world at the dark edge of the solar system would remain fundamentally mysterious because the technology to study it properly did not exist. Then James Webb arrived. And when it finally pointed its mirrors at this frozen, distant dwarf planet and took measurements in a range of light that no instrument had ever successfully captured from Pluto before, what came back stopped the lead scientist in front of his colleagues and made him say something that had never been said about any world, anywhere, in the history of planetary science. This is unique in the solar system. Not rare, not unusual. Unique. And that was only the first discovery. Because while the first set of papers was still being published, Webb had already found something else, a substance sitting on Pluto's surface that also appears on Titan, Saturn's largest and most studied moon, 4 billion miles away in the opposite direction. A substance that matches absolutely. Nothing in the entire database of known chemistry. Scientists cannot identify it. That paper appeared in July 2026. The finding is 1 month old. This is the full story of what Webb actually saw, how it saw it, and why a frozen dwarf planet that got stripped of its planetary status in a vote that made the internet angrier than almost any scientific decision in living memory has just become one of the most scientifically important objects in the solar system. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at Lowell Observatory in Arizona. He found it by comparing photographic plates taken nights apart, looking for a point of light that had moved. For 76 years, it was the 9th planet. Then in 2006, the International Astronomical Union redefined what a planet is, and Pluto lost the title. That debate has never fully settled inside the scientific community. But the classification argument was never the most important question. The most important question was what Pluto actually was. And for most of the time since its discovery, that question simply could not be answered. Pluto is too small, too far, and too cold for most telescopes to study meaningfully. Even Hubble, at its best, produced blurry, pixelated outlines. Astronomers knew Pluto existed. They knew its approximate size. They knew it had a large companion moon, called Charon, discovered in 1978. They knew it had a thin atmosphere detected in 1988 when the dwarf planet passed in front of a background star and dimmed it in a way that proved something gaseous was there. But the actual nature of that world was a mystery for decades. Everything changed on July 14, 2015. After 9 years of travel, NASA's New Horizons spacecraft made its closest approach to Pluto, coming within 7,800 miles of the surface. What it found was not a dead, frozen rock. It found nitrogen ice plains so flat and geologically young that something must be actively renewing them, a process that should not be possible this far from the sun. It found mountains of water ice rising, 3 kilometers above the surface. It found a bright heart-shaped basin called Sputnik Planitia that has become one of the most recognizable features in the outer solar system. And it found an atmosphere, thin and layered, wrapped in a blue haze that scattered sunlight in a way that made Pluto's sky the same color as Earth's when viewed from the right angle. New Horizons proved Pluto was geologically active, doing things no model of a small icy body in the outer solar system had predicted. But New Horizons was a flyby. It had hours, not months. Its instruments were designed for a mission planned in the 1990s. And the biggest limitation was in the mid-infrared, the range of the electromagnetic spectrum from roughly 5 to 27 micrometers in wavelength, where the clearest molecular fingerprints of Pluto's surface chemistry and atmospheric composition would show up. No instrument sensitive enough to detect those signatures from Pluto's distance had ever existed. Astronomers built theoretical models, made predictions, wrote papers about what they would find if such an instrument ever became available. Then they waited for James Webb. The first observations of Pluto using JWST were made with its MIRI instrument, the mid-infrared instrument, in 2022 and 2023. Results were published in 2 papers in April and June 2025, in Astronomy and Astrophysics and Nature Astronomy by an international team led by Tanguy Bertrand of the Observatoire de Paris. The mid-infrared matters for Pluto specifically because different molecules absorb and emit infrared light at very precise wavelengths. Those wavelengths are like molecular fingerprints. When you look at an object in the mid-infrared, you can identify exactly what chemicals are present on its surface or in its atmosphere by matching the pattern of absorption and emission against known compounds in the scientific literature. The mid-infrared range is particularly rich for the kinds of organic chemistry and icy compounds expected on Pluto. But detecting those signals from something as cold, small, and distant as Pluto requires sensitivity that is almost impossible to engineer. Every previous instrument that had tried had failed to separate Pluto's signal from Charon's. James Webb achieved it, and the data revealed something nobody had predicted was the dominant feature of Pluto's climate. In 2017, a planetary scientist named Si Zhang at the University of California, Santa Cruz proposed what he called a crazy idea. He argued that Pluto's atmosphere was not primarily controlled by its gases, the nitrogen, methane, and carbon monoxide, that make up most of what is there. He argued it was controlled by haze, fine organic particles suspended high in the upper atmosphere, absorbing sunlight and radiating it back as heat, acting as a planetary thermostat. He predicted that if this haze was doing what he thought, it should be emitting detectable mid-infrared radiation. Nobody could test this prediction in 2017 because the telescope capable of doing it did not exist. When Webb's 2025 papers were published, Zhang's hypothesis was confirmed completely. In planetary science, it is not common to have a hypothesis confirmed so quickly within just a few years. We feel pretty lucky and very excited. What the data showed is this. Pluto's atmosphere contains haze particles that rise and fall as they are heated and cooled. The haze particles control the energy balance of the atmosphere as they heat up and cool off. That is very unusual and has not been seen in other solar system worlds. Every other atmosphere ever studied across every planet, every moon, every body, anywhere in the solar system is primarily regulated by its gases. Nitrogen regulates Earth's. Carbon dioxide regulates Mars. Pluto is regulated by solid organic particles suspended in the upper atmosphere. Not gas, haze. A layer of tiny particles is doing the job that molecules do everywhere else. This is unique in the solar system, said Tanguy. Bertrand, the astronomer at the Paris Observatory who led the analysis, his team's Webb observations show Pluto running a climate system that shares no obvious parallel with any other world in the known solar system. The haze is cooling Pluto's upper atmosphere by about 30 degrees Celsius, more than gas-only models had ever predicted. On a world where the surface temperature is around minus 230 degrees Celsius, that is an enormous effect. Every atmospheric model ever built for Pluto had the driver wrong. Not wrong about the gases or the surface chemistry in isolation, wrong about what was actually running the system. The driver was invisible to every instrument that had ever looked at Pluto before Webb. But the haze is not just cooling Pluto's atmosphere. It is simultaneously doing something else. By absorbing ultraviolet sunlight, haze particles also gain enough energy to kick methane and other organic molecules out into space. Pluto's haze is energizing its own atmospheric material and driving it across the gravitational boundary between the two worlds. And Charon, Pluto's companion moon, is absorbing it. Charon is stealing Pluto's atmosphere. Not quickly, not in any single dramatic event, continuously. Over billions of years, molecule by molecule, the haze is driving Pluto's material across space, and Charon is collecting it at its poles. The dark reddish stains on Charon's polar regions, the features that puzzled scientists when New Horizons photographed them in 2015, are Pluto's material. Organic molecules that escaped Pluto, crossed the void between the two worlds, settled on Charon's poles, and were then transformed by solar and cosmic radiation into complex reddish organic compounds called tholins. What looks like a geological feature on Charon is actually a record of billions of years of atmospheric transfer from a neighbor 12,000 miles away. This eerie interaction happens nowhere else in our solar system. No other moon and planet pair has this dynamic. Two worlds in active chemical conversation across space, connected by a continuous flow of molecules driven by haze physics that we only just confirmed exists. JWST's close study of Charon also revealed hydrogen peroxide on its surface, alongside ammonia and crystalline water ice. Hydrogen peroxide forms when light and radiation interact with water ice, which means active surface. Chemistry is ongoing on Charon right now. On a moon with no internal heat, no liquid water, no atmosphere of its own, radiation is continuously processing the material on its surface and generating new compounds. Charon is a slow-motion chemistry laboratory running on cosmic radiation in total cold, steadily manufacturing molecules at the edge of the solar system. And then came July 2026. Scientists detected a weak and narrow absorption feature at 5.11 micrometers on the surface of Titan using JWST's NIR spec instrument. They then found the exact same absorption feature in the JWST MIRI spectrum of Pluto, centered at the same wavelength but significantly wider than on Titan. The team compared the signal against every known atmospheric gas, every known haze particle, every known ice or organic compound in the scientific literature. Nothing matched. An unknown substance on the surface of two of the most studied worlds in the outer solar system, appearing at the same precise wavelength, matching nothing in the catalog of known chemistry. The depth of the absorption is similar on both worlds, around 4 to 7%. But the width of the feature on Pluto is roughly 3 times broader than on Titan. Same molecular fingerprint, different width. That difference is meaningful rather than confusing because it tells researchers that the compound behaves differently under the distinct surface conditions of each world. Titan has a thick nitrogen atmosphere and lakes of liquid methane. Pluto has a thin haze atmosphere and nitrogen ice plains. The fact that the same unknown substance appears on both worlds under completely different conditions suggests it forms through a common chemical pathway that operates broadly across the outer solar system, not something requiring a single specific local environment to exist. Scientists are now running laboratory experiments to find which candidate molecule, when tested under Titan and Pluto surface conditions, can reproduce the spectral fingerprint. The NASA Dragonfly mission, a nuclear-powered rotorcraft, designed to fly through Titan's atmosphere and land at multiple locations on its surface, is scheduled to launch in 2028 and reach Titan in 2034. When it does, it will be able to directly sample whatever this substance is. But that is 8 years away. For now, an unknown molecule exists on at least 2 worlds in our solar system, and science cannot tell you what it is. Now step back and look at what all of this means together. Pluto runs a climate system found nowhere else in the solar system. Its haze simultaneously cools its upper atmosphere, feeds molecules to its companion moon, and is made of chemistry that connects it to Titan across billions of miles of space. And sitting on its surface is an unidentified substance that appears on one of the most heavily studied moons in planetary science and matches nothing currently in the database. The connection between this frozen dwarf planet and questions about the origin of life on Earth is direct, not speculative. Before oxygen transformed our planet's atmosphere roughly 2.4 billion years ago, Earth was wrapped in a haze of organic particles, a nitrogen and hydrocarbon chemistry strikingly similar to what Webb has now confirmed at Pluto today. That early haze may have played a role in stabilizing Earth's temperatures and creating the conditions in which early life could develop. General circulation models that include aerosol physics already show that fine particles can swing global temperatures by dozens of degrees on young Earth-like planets. Pluto is now the first natural laboratory where haze-dominated atmospheric physics can be observed directly and tested with the same telescope being used to study exoplanet atmospheres. Because Pluto orbits the Sun once every 248 Earth years, JWST snapshots in 2022 and 2025 sample only the early stages of a long Arctic winter at its North Pole. Scientists expect the haze thermostat to work even harder as the Sun dims, a forecast Webb will be able to test across the next decade. For the first time in the history of Pluto research, there's an instrument capable of watching this world change in something approaching real time. Not over geological ages, not over centuries. Over years, the timescale on which a single observatory operates. Pluto waited 95 years after its discovery for a telescope powerful enough to read what was written on its surface and in its atmosphere. James Webb finally did it, and what was written there was not a frozen relic unchanged since the early solar system. It was a unique climate, a living chemistry, an atmospheric theft playing out over billions of years, an unknown molecule matching nothing in science. And a connection to the question that started all of this in the first place. How did life get started on Earth? That answer, if it exists, is sitting 3.67 billion miles away. And we're only just beginning to read it.